Hi again everyone, I'm Tisdell, and in this video I'm going to show you why the directional derivative of a function of two variables is a certain dot product. Now in previous videos I've shown you many examples where we calculate the directional derivative of a given function in a particular direction, and I've also given you some geometric explanation of what the directional derivative represents. Now this video is a little bit different and in particular we're going to prove the following result. Suppose I have a function of two variables and that function is differentiable, say everywhere for all x and all y. Then the derivative of f at a point P in its domain in the direction of a unit vector u hat is defined to be this limit. Okay, so you can see I've got the limit of this difference quotient, if you like. And in particular, I claim that this, under these conditions, this limit can actually be computed by taking this particular dot product. Okay, so let's talk a little bit more about the details here. By this u hat, I mean a vector of length or magnitude 1. So by these pairs of vertical lines, I mean the magnitude or the length of a vector. Now by this nabla here, I mean the following special vector. Essentially you take the partial derivatives df dx and df dy and you write them as a vector. Okay, so sometimes we refer to this as grad f, or the gradient of f. Okay, so I'm going to show that under these conditions this limit is actually equal to this dot product. Now firstly, why would we want to do that? Well, this limit may not be so easy to calculate. Okay, whereas it's very easy to calculate the partial derivatives and take a dot product. So from a computational point of view, what we would like to do is use this right hand side wherever possible. Okay, so let's have a look at the proof. Oh, actually before I get to that, in some of my previous videos and in some of the literature, the notation for the directional derivative of a function f in the direction of a unit vector u at a point, say P, is just this sort of doof P. Okay. Now, essentially the relationship may be formed by using the concept of differentiability of a function of two variables. So that's the key concept to the proof, really. Now, I've shown you in other videos how differentiability can be used to prove a chain rule. Now, hopefully you're getting the idea that differentiability is a really desirable thing because we can do lots of things with differentiable functions. Okay, so since f is differentiable, we can write this difference here in the following way. Essentially, we can write this difference in terms of partial derivatives and certain functions epsilon sub 1 and epsilon sub 2. I can write it like this. Okay, so this difference can be written in terms of the following. Now, these, as you can see, basically we're just taking the partials and multiplying them here by the difference in the arguments. And I've got these two terms over here, which is epsilon sub 1 times the first difference plus epsilon sub 2 times the second difference. Okay. Now, the epsilon 1, the functions epsilon 1 and epsilon 2 satisfy the following conditions. They go to 0 as the difference goes to 0. Okay, so what I'm going to do now is just consider this, forget about the limit for a second, just consider this quotient with the top replaced by this. So if I divide everything here by s, you can see I'm going to get a lot of cancellation. Okay. Okay, so if I divide, just use this thing and divide by s, then I'm going to get something like this. Okay, so now what I'd like to do is show that I'll basically take the limit as s goes to 0. Okay, so let's take the limit of s goes to 0. Well, this doesn't depend on s and neither does this, so they're going to stay the same. What happens to these two terms? As s goes to 0, if s goes to 0, but definitely s times u1 is going to go to 0. And if as s goes to 0, s times u2 is going to go to 0. So essentially, if s goes to 0, these two terms are also going to go to 0. And if you look carefully at this, what is this? Well, it's just this dot product. So it's just the right-hand side of the expression that we were trying to prove. Okay, so you can see, hopefully, that the proof relied very much on the differentiability of f. Okay, so we wrote this, the difference up here as the following in terms of the partial derivatives, and then we let divided by s and let s go to 0, and we know that these two terms disappear, and then just wrote this as a dot product. So that's a proof of the connection between the directional derivative of a differentiable function and a particular dot product involving this unit vector and the gradient.